Hello and welcome. Today's lab is about magnetic field on bar magnet. This is the third lab in our course. In this lab, our objective is to find the correlation between magnetic field and observable distance. The main objectives are to compute the magnetic dipole moment of a bar magnet, and then make computational model for magnetic field around bar magnet, and then we just compare the previous two. We use Boas-Sabart's law to find the correlation between magnetic field and observable distance. We use the concept of superposition as well. Before doing the lab, I gather my lab materials, a phone, then a stick, then a bar magnet. We download the magnetometer app, find magnetometer chip inside my smartphone, and then before proceeding to the rest of the lab, I would need to identify where exactly on my smartphone the magnetometer sensor is located. This location will vary between makes and models of smartphones, but it should still be the same, and it should still provide us pretty good accuracy. We basically find different magnetic field at different R values to solve for N in the equation shown. We find the distance from the magnet to the sensor that produces a magnetic field with an X component of magnitude 20 microtesla. We basically call this distance R20, and then we repeat this process for different R values 2 more times, and we basically find the rest of the data in a similar manner and put it on the Excel sheet. At the end of the day, we end up with an average B-net magnitude of 5.3 times 10 to the power negative 5. It's quite difficult from an initial plot to tell exactly what the experimental value of N is, unless I use a curve fitting software. Therefore, we take the logarithm of both sides, and then the slope of the line becomes the N value. Logarithm of k is the y-intercept of the line, while n is the slope of the line. And then we move on to using the Boas-Savart law to measure the magnetic field from an off-axis location. We find the magnetic dipole moment to be 2.33. The GlowScript code starts with a function called dipole B, which is essentially an implementation of the Boas-Savart law that we learned in our class, but in a program, to the magnetic field calculations off axis. We move on to calculate the observation locations, and then we make sure that they're always at the magnitude of distance away from the origin. We find the experimental magnitude to be 5.37 times 10 to the power negative 5, while we find the computational magnitude to be 6.34 times 10 to the power negative 6. The two values are a magnitude of 10 off, so there's a lot of discrepancies between what we get from experimental and computational. This is the simulation of the bar magnet. The orange arrows represent the on-axis, while the ACU ones represent the off-axis ones we calculate from the Boas-Savart law. The pink one represents the 45-degree angle arrow, and I noted the experimental and computational magnitudes on screen again, and the huge discrepancy might be just due to human error or not ideal conditions. And then we move on to conclusions. For conclusion, question number 1, what if you hadn't oriented your experiment to compensate for the magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would the results have changed? All the readings would be skewed to the north anyway. We would have to sacrifice on accuracy. Our magnetic dipole values would change, our K values would change, our N values would change. Everything would change. For the second question, what if you were to stick two identical magnets together, end to end, and run the experiment again? How do you expect the measurements to differ? The directions would stay the same while the magnitude of the magnetic field would just get doubled, uh, approximately doubled. Well, that's it for lab 3, and see you next week.